All right, so your test will be through 210, which we're starting when? Today, right now. That's awesome. Good. It's always good to learn the material before I test you over it. It's kind of a nice sequence. This is a log, right? But it's a double entendre log, because if you follow this little branch up here, which kind of goes up and to the right, it also looks like the shape of what a logarithmic curve resembles, which, of course, you know. Come on in, Bradley. We're just starting this section. I'm glad someone went out there to get you. Dang it. Well, you know what? You didn't miss much. I'm really sorry about that. We were looking at Google Earth, actually. Yeah. There's some salt mines in Botswana that are just beautiful to look at. Anyway, a log graph, remember, has a vertical asymptote on the y-axis. I got to tell Miss Cooper thank you next time I see her. Did you tell her thank you? Yeah. Gosh, dang it. One day I'm going to remember that I have a student out in the hall. One day. Anyway. Logs, right. Yeah. Logs are the inverse functions of what functions that we've studied? Logs undo the work of what? Exponentials, right. Okay. Log functions are the inverse of exponentials. In fact, this is the way that you go back and forth between logs. We're going to kind of jump around here today. This, for lack of a better word, is the conversion theorem. It allows you how to regroup your sentence, your mathematical sentence structure, to get an equivalent statement, one in terms of logs, one in terms of exponentials. So b to the x equals y if and only if, that's how we read the double-headed arrow, log base b of y equals x. It's bidirectional. So if we start with the bottom, log base b of y equaling x, that's true if and only if b to the x equals y. So you can convert, if you want, from one form to the other. This b here and this b here, they're the same base, exactly the same base. And of course, we know that there's only certain values it can take on. If the base is greater than 1, you have growth, whether it's exponential growth or logarithmic growth. If the base is between 0 and 1, you have decay, either exponential decay or logarithmic decay. Those are the only allowable bases. But notice that the log is x, right? The equal sign means is. The log is x, and the x in the top part is the what exponent? The exponent. So that's really all a log is. A log is an exponent, but it's not an arbitrary exponent. A log is the exponent to which you must raise your particular base to achieve your desired result. And your result in this case is y. It's called the argument. And this x is, of course, the log itself. So you can think of going from one to the other by using like the around the world. B raised to the x power equals y. B to the x equals y. But it's probably best that you just understand how it all fits together. Let's work an example here real quickly. Log base 2 of 8 is equal to some other number. Okay? So if you want to know what it's equal to, we'll put equal to. Now remember, the log is the exponent. So we're looking for the exponent to which we must raise the base of 2 to achieve our desired result of 8. In other words, 2 to what power is 8? 3. You're done. So log base 2 of 8 is also known as 3. You can write it like this as well. Log base 2 of 2 cubed, right? That's another name for 8, 2 cubed. And now we're into this property that says log base b of b to the blob is just the blob. Because if you start with the 3 and you exponentiate it base 2, and then turn around and log it base 2, guess what's going to happen? You're going to end up right back where you started. What logs do, though, is they cut numbers down to size. They do a great job of making big things small, or like microscopic things that are small a little bit bigger. So in this case, instead of looking at 8, we can look at its exponent 3. And that's exactly why logs were invented, to look at relative sizes. Blah, 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 blah. Let's look at limits. Limits are important. So example 3. These are calculus questions without having to do the derivative. The limit as x goes to infinity of the natural log of x squared minus x. How would you evaluate that? These make wonderful multiple choice questions. part E's on free response questions, last little bits. Could you use direct substitution? Never, not first, right, for limits? What do we get when we plug in infinity? We get the natural log of infinity squared minus infinity. Is it infinity? Yeah. Well, of course, remember, if we did plug it in here, we don't have to worry about the minus x, correct? Because when we're going to infinity, we're looking at the end behavior, and x squared minus x is dominated by the leading term. So infinity squared is infinity. So this is approaching the natural log of infinity, which, yes, the natural log of infinity, if you look at the graph, we're really saying what's the limit as x goes to infinity on the natural log function. And it does go up forever and ever and ever and ever and ever. So, of course, a safe answer, whether you know the answer to be infinite and non-existent, or whether you're in doubt and you live by the motto, when in doubt, DNE, right? DNE is the correct answer. But the better answer would be infinity, because that says why it's undefined. Okay, how about this one here? The limit as x goes to 9 from the right of log base 2 of x minus 9. Well, what do you get when you plug in a 9? You get log of 0. What is log of any base of 0? Log of 0? It's DNE because it's some type of infinity. That's where the vertical asymptote is. Okay, so if you know that, when you take log of 0 at some type of infinity, you could say DNE. But because it's a one-sided limit at a vertical asymptote, that would not be the multiple choice answer. But at least you would know it's either positive or negative infinity. So, how would you guess which one? What criteria do you use for guessing? Do the what? Yeah, that's, you don't guess at all, right? You don't guess at all. You actually figure out by plugging in a number just to the right of 9, like 9.1. Good. Don't go so far to 10. 9.1 minus 9 is 0.1. Now, if you take log base 2 of like 0.1 or 0.01 or 0.001, whatever, what's that going to look like? Well, remember log base 2 looks almost exactly like the natural log. It's gross. And 0.001 is going to be just to the right of the vertical asymptote, which puts you way down there for a y value, yes? And if you get a little bit closer, then it's going to be even further down. So guess what the answer is? When you're just to the right of the vertical asymptote here, you're at negative infinity. Now that's one way to do it. The other way to do it is just saying, oh, log base 2, that's gross. What does the minus 9 do to my graph on any function? Shifts it to the right 9 units. So the old vertical asymptote, which is at 0, is now at 9, and now it looks just like that. And what are we approaching as I get closer and closer to 9 from the right? I'm going down, 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 to negative infinity. Yep. What if this had been, instead of log base 2, what if it had been the exact same question, but instead of base 2, it was base 2/3? Would that be logarithmic growth or decay? Decay. Would it still be shifted to the right 9? Yeah, so you still have a vertical asymptote here at 9, but now it's going to look like this. And what would be the limit as we approach 9 from the right? Positive infinity. Would DNE still be an acceptable answer on a free response? Yes. Okay, how about this one? You go. Take 1 minute. Anyone in doubt? You should be living by that when it comes to limits, right? When in doubt, D and E. Because things can fail to exist for several reasons, so it is kind of a catch-all category. This one is also D and E, but not because anybody's in doubt. Remember, the limits are those things that we can kind of reproduce and take inside. So when you have a composite function, you could just rewrite it if you want, log, and then take the limit inside. And now you're focusing on the limit as x goes to pi halves of tangent. Well, tangent of pi halves is undefined. Do you remember that from the unit circle? There's a vertical asymptote there. Here's what the graph of tangent looks like, and you should know that. It's a monotonic increasing function. It passes to the origin. The first vertical asymptote is at pi halves, and then it starts again. So if you're approaching pi halves from the left, that's approaching your first vertical asymptote from the left. It's going to infinity. So now you could just say log of infinity, but what you're really doing now is, remember, that output of infinity becomes the new input that you're approaching. So now it's technically the limit as x goes to infinity of the next layer, which is log of x. And of course, what's the base there if it's log but not written? 10, which is growth, so it looks just like the natural log essentially. And as you go out to the right, you're going up, 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 forever and ever. So the answer is infinity. So we dealt with composition of functions earlier in the year. Now we're just doing them with logs. All right, very quickly this one here. Let's do it without having to rewrite it. Plug your 0 in first. What's cosine of 0? 1, right? So then it becomes log of 1. What's log of 1? 0. Did direct substitution work? Yeah, never not first. Okay. Finding domains of functions. Example 4. In general, we don't want to take the square root of a negative, divide by 0, or in this case now, take the log of anything that's not positive. So if you ever are asked to find the domain of a log function, or you're working with a log function and you need to know its domain, the simplest way to find it is to take the argument, which is the thing you're taking the log of, and say it's strictly greater than 0. And then you solve. So let's do that here on part A. Our argument is the quadratic, x squared minus 3x plus 2, and it has to be positive. By the time we're done picking x's and squaring them and subtracting them from 3 times itself and adding 2, it better be a positive number. So rather than guess and check, we'll solve this. Now, we can only solve certain inequalities purely algebraically, and those are linear. Is this a linear inequality? No. So we solve these some other way, and the easiest way is graphically. So what do I know? I know that it's a parabola that opens up. I know that just by looking at it, right? Positive coefficient x squared. And so the x-axis might be right there. If I want to know what values of x are going to give me positive parabola values, well, that's going to be above the x-axis, yes? I already know then that it's going to be everything to the right of that x-intercept and everything to the left of that x-intercept. Because your solution, if you recall, is either going to be between the x-intercepts or outside of them. So all I got to do is find the x-intercepts. Well, to do that, I'm going to factor it. X minus 2, x minus 1. Now, you can still have the product greater than 0. Here's where it breaks down. If you say x minus 2 is greater than 0, or x minus 1 is greater than 0, that's where it doesn't work. And that's where students get confused. It's either greater than 1 or greater than 2. Well, I guess it has to be greater than 2, because everything greater than 2 is greater than 1. So that's your answer, and that's wrong, right? That's wrong. So what you do instead is you realize that, this must be x equals 1, and this must be x equals 2. Those are my x-intercepts. And I'm going to get positive values outside of there, so my domain is going to be everything less than 1 or less or greater than 2. So the x being greater than 2 was part of it, but you missed the whole other part less than 1. Okay, now that's good to know because it'd be kind of silly to be talking about a graph where it doesn't exist, right? So if we were talking about the graph like at 1.5. All right, so what happens then when you plug in a 1 and a 2 up here? You're going to get log of what when you plug in a 1 or a 2? You're going to get log of 0. And what do you already say log of 0 is equal to? Log of 0 is equal to No, I wrote it up there. If you plug in a number and you get log of 0, what exists on, it's a vertical asymptote. So log of 0 is some type of infinity. It's some type of infinity because there's a vertical asymptote there on the graph. So I don't know what the graph looks like of log base 10 of the parabola, but here's what I do know based upon this limited information. I know that at x equals 1, there's a vertical asymptote, and I know at x equals 2, there's a vertical asymptote. And I know that the graph lives to the left of 1 and to the right of 2. That's all I know. I'm going to write in some questions here, follow-up questions. Part B, what would be the limit then of that function as x approaches 1 from the right? Well, if you use direct substitution, you're going to get log of 0, which you realize is undefined. So dne is not a bad answer. It's undefined. But if it's positive or negative infinity, you want to do better than that. Well, can we do better than dne? If I'm approaching 1 from the right-hand side, look at what we just said. We just found the domain and said it only lives to the left of 1 and to the right of 2. Can we even be approaching 1 from the right-hand side? No. So this one is dne. There's no other thing it can be, right? It's dne because the graph doesn't exist there, which is why dne is a good catch-all category if you're not sure. Now, perhaps a better question, a more meaningful question would be the follow-up here, which I'll add. What would the limit be as x approaches 1 from the left-hand side? Direct substitution, again, would give you log of 0. Log of 0 means infinity, which doesn't exist, so dne is technically correct again. But now, since the graph lives there, we want to do better than that. In other words, as I approach 1 from the left, is it going up to infinity or down to negative infinity? How could I figure it out? How have we always done it? Yeah, plug in a number just to the left of 1 and c, like 0.99. Now, I don't want to have to come up here and plug a 0.99 in there, right? 0.99999 squared. So now I'm just going to guess infinity. No. Remember what this graph over here was? This was a parabola. This represents your argument. If you pick a number just to the left of 1, like 0.999, what type of y value are you going to have right here? Just to the left of 1, you're going to have a very small positive y value. You see that? Your y value on your parabola is going to be very small positive. Okay? So what that means then is you're going to be taking the log base 10 of a very small but positive number. That's all you need, right? Think about what the graph of log base 10 looks like, or log of any growth function. They cross right there at the point 1, 0, and they're growth. So if you take the log of a very small positive number, what type of log value are you going to get? Really close to the vertical asymptote, your y values are extremely negative, right? In fact, they're coming from where? Negative infinity, which is the better answer. Good thing I didn't guess positive infinity. Let's do this follow-up question here. What would be the limit as x approaches 2 from the right-hand side? If I use direct substitution, I get log of 0, because it's the other x-intercept. What's log of 0 mean? dne, vertical asymptote, so again, a safe answer. But because it's a one-sided limit, I know it's going to be some type of infinity, plus or minus, plus or minus, plus or minus. Which one? Plus, because if it's negative on one side, it's got to be plus on the other, right? That's what I read in the newspaper. Nope, that's not necessarily true. We better do the same thing, huh? Let's plug in a number just to the right of 2, like 2.00000000001. And again, I'm not going to bother squaring that. I'm going to go to my graph right here of the argument. If I choose a number just bigger than 2, my parabola is going to have what type of y value again? small positive y value, and I will be taking log base 10 of a small positive y value, which is going to give me what type? A number? A super negative number. It's negative on both sides. So we know now without the calculator that this graph is doing something like this. It looks like a log function going up to infinity on the right, and it kind of looks like a log function going up to infinity on the left. We know that already. Which helps us answer this one. What would be the limit as x goes to negative infinity? Well, if this graph is correct, up on the graph, where are we going? Yeah, we're going up to infinity. Or, of course, dne. Well, what if we didn't know that graph? End behavior is real easy to figure out. Here's what we do for that if we're not sure. We'll come back to the equation, if we can find it. And remember, if you use direct substitution, you don't need to plug it into all that. For end behavior only, you can look at the leading terms, right? We're going out to the left. What's negative infinity squared? Positive infinity. And what's log of infinity? Log base 10? Infinity. So it goes up to infinity. So you can do it like that and get the same answer. Nice. Love these logs. Okay. Here's what makes logs so useful. And we're getting closer to the calculus part. Logs take everything down one rung on the operational ladder. They turn multiplication into addition. They turn division into subtraction. And my favorite, they turn exponentiation into multiplication. So these are the rules you had in Algebra 2/Pre-Cal. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. And the log of a power is the product of the power, which becomes a constant multiple, times the log. I love this one here. It's very useful. Okay, let's jump down to example 6. We're going to bust out the calculus. It says if y equals the natural log of x, solve for x, then find the derivative of y using implicit differentiation. Wow, that's a huge clue. It's a huge clue, because without that clue, if they just wanted me to find dy dx, I might have not been able to do it. Here's what the graph of the natural log of x is. By the way, the natural log of x is really the same as log base what? E, right? Where e is about 2.7, so it is growth. It passes to the point 1, 0. Once we have the graph, we can start talking about how fast it's changing, right, at certain values. So we would need to know the slope of the tangent line. And for that, we need the derivative. Well, I don't think I can find the derivative of the natural log of x on my own. None of the rules we've memorized so far seem to work. But here's what I can do. I can solve that for x. How do you unnatural log something? What's the inverse of log base e? Exponentiate base e. So you could do this one of two ways. You can exponentiate both sides, and that's what it would look like. So the two sides now become exponents. We would read that now as e to the y power equals e to the natural log of x power. They have to be written kind of like bases. Now, of course, we would have e to the y on the left, but what is e to the natural log of x power? It's x, right? Because, again, that's e to the log base e of x, which is x, which should be the same if you did it the other way around as well, log base e of e to the x. So that's one way to do it. The other way to do it is to call the natural log base e of x, and then you could do the around the world thing. The conversion, you could say e raised to the yth power equals x. You get the same thing. I kind of like the exponentiation. It's more algebraic. Now what I can do from here is I can take the derivative of both sides with respect to x. It's no longer solve for y, but I know that that's not a big deal anymore because I know how to take the derivative implicitly. And it's actually better for me because I put it in terms of e, which I know how to differentiate, rather than ln, which I don't. So take the derivative of both sides with respect to x, and here we go. On the left side, this could have been on the quiz. It wasn't, but it could have. But it wasn't. The derivative of e to the yth power is e to the yth power times the chain rule, dy dx. Yeah, okay. And then on the right-hand side, the derivative of x with respect to x is 1. Now I just got to solve for dy dx. So I'll divide both sides by e to the y, and I get 1 over e to the y, which is great. Because here's what I just discovered. The derivative with respect to x of the natural log of x is e to the y's power. You know, it's nice, but there's something that I don't like about it. It's in terms of y, and we started off in terms of x. It'd be nice to write the derivative also in terms of x, wouldn't it? But to do that, I would have to know what y, e to the yth was in terms of x. Do we? I think it's x, huh? So here's the better version. The derivative, it's 1 over e to the y. So it becomes not 1 over e to the y, but 1 over what e to the y is equal to, which is x. And there it is. Wow, that's awesome. I would memorize that, okay, if you haven't already. What's the derivative of natural log of x? 1 over x. Yeah. And 1 over x is a parent function also, right? We know what it looks like. What's the domain of our function that we're starting with? Of any log function? Log of x? Take your argument, x, and say it has to be greater than 0 and solve. They have to be positive, right? What's the domain of 1 over x? It can be positive or negative. It just can't be 0. Now, here's the thing. When you're starting with the natural log of x, you have to use its domain, even when you take the derivative. So the derivative of the natural log of x will be 1 over x, but we're going to limit ourselves to positive values. Values of, again, that actually work. Here's why. You don't want to be talking about the slopes of a function where they don't even exist. I'm going to sketch the natural log of x here in purple. Now here's what I'm going to do. On the same grid, I'm going to attempt to sketch the graph of its derivative in green, which would be 1 over x apparently. Well, actually, I know what the graph of 1 over x looks like, right? That's your parent function. It looks like this. And there's a horizontal asymptote. But there's also another branch of 1 over x over down here. The only thing is, if I'm starting with the natural log of x, I don't even use that second branch of 1 over x. I'm just looking at the green graph here. Now, this is the first time we've done something like this. We're looking at the purple graph and its derivative, the green graph, on the exact same coordinate plane. So the y values of the green graph represent the slopes of the purple graph at those x values. Would you agree? Let's make the connection. I've got my virtual curve surfing surfboard here, okay, a meter stick. I'm going to analyze the slopes of the purple graph. First of all, I'm going to note that the purple graph is monotonic what? Increasing. And so its slopes are going to be what? Positive or negative everywhere? Positive. So the y values of its derivative, which are in green, are also going to be positive y values. That's why they're above the x-axis. Got it. Now I'm going to see how are they positive. As I come in from the left, the slope of the purple natural log graph is super, super steep, right? And it's positive. It could be like 1 billion. So at that value of x, where it's tangent, I need to plot a y value of 1 billion. Well, where is that going to be found? Way up there, right? So as I go to the right now, my slopes are still positive, but the slopes themselves are decreasing. 1 billion, 1 million, 100, 5, 4, 3, 2, 1. 1/2, 1/4, 1/8, 1/16. What are they approaching, my slopes? They're approaching 0. Will they ever reach 0? No, because this thing goes to infinity. So here's what you're telling me. I need to have my y values of my derivative come from some huge positive number, like from infinity. It needs to gradually and slowly decrease, approaching 0 but never equaling 0. Okay, here's positive infinity. Let's go downhill. We'll stay positive. And now I'll taper off and approach 0. There you go. That's the derivative, and it makes sense now graphically. Okay, cool. What's the derivative of the natural log of x? 1 over x. All right, let's step it up here a little bit now. What if I asked you to sketch by transformation the following graph? Do you remember how to sketch a function with that transformation when you're taking the absolute value around the x? Jump? Should it have any symmetry by design? What kind? It should have y-axis symmetry, good, by design. Because remember, y-axis symmetry means positive x's and negative x's graph the exact same way. And because this is taking the absolute value of your x, the natural log of 1 should equal the absolute value of negative 1. The natural log of the absolute value of 2 is the same as the natural log of the absolute value of negative 2. So at 1 and negative 1, they're going to have the same y value. At 2 and negative 2, they're going to have the same y value. The way we sketch that, if you recall, is number 1. We leave positive x's alone in quadrants 1 and 4 because the absolute value of a positive number is positive, right? But what happens over here in negative x land in quadrants 2 and 3? Any graph that might have lived there is gone. In this case, there was nothing there. And because they have y-axis symmetry, we take the positive x graph in 1 and 4 and we reflect it across the y-axis. So this purple graph would reflect like that. And now both of these branches in their entirety become the graph of the natural log of the absolute value of x. What's the x-intercept over here on the left side? Negative 1, because it's positive 1 over here. The natural log of the absolute value of negative 1 is the natural log of 1. Okay, so if I then wanted to talk about the slopes of my new purple graph, over here in positive x land, it would be the same argument, wouldn't it? This green graph would be its slopes, yes? But if I wanted to talk about the slopes of the purple graph over here on the left side, notice this purple piece is monotonic what? Decreasing. So my slopes are going to be negative. So I should have negative y values. How are they negative? Well, they're coming in here like negative 1/2, negative 1, negative 5, negative 10, negative 100, negative 1,000,000, negative 1,000,000,000, approaching negative infinity. So my y value should come in from something that's approaching 0, should be negative, should be decreasing towards negative infinity. Look what the y values do on this other branch of 1 over x. They're negative, and they go down and approach infinity. Based upon that, it looks like the other branch of 1 over x is a perfectly suitable derivative for the natural log of the absolute value of x. So if we just learned this a little while ago, to be 1 over x, of course, we have to stay in the domain of the natural log of x. It would appear, graphically at least, that the derivative of the natural log of the absolute value of x is what? These green values are good slopes for the purple graph, and over here, those green values are good slopes for the purple graph. So it appears that it's the same thing. We just got, well, not just less than 0, we can actually use everything but 0, right? We've expanded our domain. And believe it or not, that's true. We'll prove it analytically tomorrow. But this is one of the few times where you're taking the derivative of something that has absolute values, and they just go away when you take the derivative. They just go away when you take the derivative. Okay, cool. Tomorrow we will pick up with example 7, which is proving this. Have a good day.